In this course, we'll be covering data structures and algorithms in C#. The course will primarily cover collections and generics, arrays and array lists, basic sorting algorithms, searching algorithms, stacks and queues, the bit array class, string class, pattern matching and text processing, dictionaries, hashing, linked lists, binary trees, sets, and sorting algorithms. We'll also cover data structures and algorithms for searching, graphs and graph algorithms, and some advanced algorithms. First of all, we'll be starting with collections in C#. So if defined, a collection is a structured data type that stores data and provides operations for adding data to the collection, removing data from the collection, updating data in the collection, as well as operations for setting and returning the values of different attributes of the collection. Collections can be broken down into two types, linear and non-linear. Linear collection is a list of elements where one element follows the previous element. A very basic example of this kind of collection is an array. Non-linear collections hold elements that do not have positional order within the collection. So first of all, we'll be exploring linear collections. Now there are two types of linear collections, direct access collections and sequential access collections. Under direct access collections, we have arrays, string, and struct. Now, a struct is a composite data type that holds data that may consist of many different data types. So let's go ahead and explore these in action: arrays, string, and struct. So here, first of all, we'll be taking a look at the string collection. This is a type of direct access collection, and when we define a string, it is basically a collection of characters that can be accessed based on their index. In the same manner, we access the elements of an array as well. So here we have created a string array, and this string array is containing two users, that is John and Matt, and you can see that we can access the values using their index positions, and they are all in sequence. So at 0 we have John, at 1 we have Matt, and if we have more over here, we can just go on with that sequencing like 0, 1, 2, and 3. And here we are just writing those values, users of 0, users of 1. Now the other type that we discussed was struct. Now here, if you take a look at this example first, the integer data type that we have in C# is basically a struct. So if I go ahead and say here int 32.parse, and if I take you to this definition, you can see that it is a struct data type, and this also comes under direct access collections. The only difference between a struct and a class in general is that you cannot inherit or derive a new type from a structure. So here you can see that we have created a struct called name, and this has got three attributes: first name, middle name, and last name. This is the constructor that we have, and it basically initializes all these attributes that we have: f name, m name, l name. And then we have these properties which returns first name, last name, and middle name. And then we have overridden the toString method to just return first name, middle name, last name as a full name, and here we are returning initials. So first letter of each word will be shown over here. Now in order to use this struct, you can see that we have created it over here, initialized it, and then we have passed these first name, middle name, and last name, and these two variables that we have will store full name and initials. So full name is coming from myname.toString and initials coming from myname.initials. Now if I go ahead and run this, you'll notice the output is coming as John and Matt from the array example, and then this is the full name, initial, and here we were converting integer from string. So here if I enter a string, it will be converted and printed as an integer value. Now in the next one, we'll be covering sequential access collections. Now in this one, we'll be covering sequential access collections. Let me tell you that this is going to be theoretical, as most of the topics that we'll be explaining over here will be covered in upcoming lectures as code examples. So to start with, sequential access collection is basically a list that stores its elements in sequential order. We call this type of collection a linear list. Linear lists are not limited by size when they are created, meaning they are able to expand and contract dynamically. Items in a linear list are not accessed directly. They are referenced by their position. So the first element of a linear list is, let's say, at the front of the list, and the last element is at the rear of the list. Because there is no direct access to the elements of a linear list, to access an element, you have to traverse through the list until you arrive at the position of the element you are looking for. Linear list implementations usually allow two methods for traversing a list: in one direction from front to rear, and from both front to rear and rear to front. We can take an example of to-do list items, let's say. So the list is created by writing down one item after the other until the list is complete. Now the items are removed from the list while each item is completed or finished. So a linear list can be either ordered or unordered. An ordered list has values in order and respect to each other, as in John, Jessica, Frank, Miller. An unordered list consists of elements in any order. The order of a list makes a big difference when performing search data on the list. And this is something which we will be coming up when we'll be exploring searches or search algorithms. Now there are some types of linear lists which restrict access to their data elements. Examples of these types of lists are stacks and queues. A stack is a list where access is restricted to the beginning or top of the list. Items are placed on the list at the top and can only be removed from the bottom. For this reason, stacks are known as last in, first out structures. When we add an item to a stack, we call the operation a push, and when we remove an item from a stack, we call that operation a pop. Stack is a very common data structure, especially in computer systems programming. Stacks are used for arithmetic expression evaluation and for balancing symbols among its many applications. Now, we have queues as well. So a queue is a list where items are added at the rear of the list and removed from the front of the list. Now this type of lists is known as first in, first out structure. Adding an item to a queue is called in queue, and removing an item from a queue is called a dequeue. Queues are used in both systems programming for scheduling operations, system tasks, and for simulation studies. A special type of queue called a priority queue allows the item in a queue with the highest priority to be removed from the queue first. Priority queues can be used to study the operations of a hospital emergency room where patients with heart trouble needs to be attended to before a patient with a broken arm, for example. Now the last category of linear collections are indexed collections. The first of these called a hash table, and that's what we will be covering in upcoming lectures. Now hash tables stores a set of data, values associated with a key. In a hash table, a special function called a hash function takes one data value and transforms the value called a key into an integer index that is used to retrieve the data. The index is then used to access the data record associated with the key. For example, an employee record may consist of a person's name, his or her salary, the number of years the employee has been with the company, and the department he or she works in. So the key to this data record is the employee's name. We have classes in C# which are called hash tables for storing data in a hash table, and this also will be covering in later videos. Similar to hash tables, we have another collection that is called as dictionary, which is made up of a series of key value pairs called associations. Now this structure is analogous to a word dictionary, where a word is the key and the word's definition is the value associated with the key. The key is an index into the value associated with the key. Dictionaries are often called associative arrays because of this indexing scheme, though the index does not have to be an integer. We'll be also covering dictionaries in upcoming videos. In this lecture, we'll be taking a look at how we can create our own collection using ArrayList. For that, we have created a class called collection, and if you see, it's inheriting from its base class called collection base. Now if I show you collection base, it has got this array list, which we call as inner list attribute. Now using inner list, we can have our own collections. How we can have our own collections? By creating methods. For instance, here you can see I'm saying create a function called add, which will accept a parameter of type object, and that item will be added to this inner list. Now inner list is of type array list, which is provided by this abstract class collection base, and this one resides inside system.collections namespace. Similarly, once we have added the item, we can also remove it. Now removing an item is pretty easy. Similar to add, we have remove, where we accept a parameter of type object, and the same parameter is then passed to the inner list dot remove method of the array list, and it will remove that item from the array list. Then we have clear basically clear search all the elements inside the array list. So we will be back to square one, and the contents of the array list will be deleted. Count is going to return the total number of elements that are present in the inner list or our array list. Now to implement this, we'll go to our program.cs file, and here you can see I've created an instance of the collection class that we just created. Here we have the instance name as courses, and we are adding some courses to this collection: JavaScript, ASP.NET, MVC, C#, Python. Now using for each loop, we are simply writing the course names, and here you'll notice we are finding out how many number of courses are there in the courses collection by using the count method, and then we are removing one course from the list or the collection, and then we are checking out what is the total count. After that, we are clearing it out, and then we are checking out what is the total count. Now if I run this one in over here, you'll notice initially it's printing JavaScript, ASP.NET, MVC, C#, Python. Then when we were saying number of courses, so total courses at that point was 4. We removed Python from it, the count reduced by 1, and here number of courses 3. Then we called courses.clear, and here you can see now the number of courses is set to 0. So all the items from the collections have been removed, and that's how easy it is in C# to implement data structures. Now in the next lecture, we'll be covering generics. In the previous lecture, we explored generic functions, and as I mentioned that generics are not limited to function definitions. We can also create generic classes, and in this lecture we'll be doing that. So here you can see I have created a class called LinkedList, and here using the angular brackets I've specified that this could be of any type. So representation T denotes that, and here I'm creating two attributes of this class. One is data and the other one is link. Now data, obviously whatever value we are passing to this particular linked list structure to hold, and link is the pointer to the node to which this instance will be connected. So here we have our constructor. Two things are being passed over here, data and the link. Here we are assigning it to data and link variables that we have over here, properties. Now to use this, we'll go to our programs.cs file, and here you can see I've created node 1, which contains a string object. So here the T is being replaced by string, and we are storing data as John, and then we are saying that this is the first element. That's the reason it's not holding anything. Now node 2 on the other hand, if you see, is having this data as Matt, and it's pointing to node 1. So if you imagine it's now connected with node 1. So in sequence, if you go node 1, then node 2, you know that node 2 knows that I'm pointing to node 1. And here we are just taking that as an example. We are using the node2.link and getting that object which the node 2 is pointing to, in a way node 1. And we are just writing it in the console. We're saying print node 1 data, then print node 2 data. So this one is going to print John, this one will print Matt, and here this third one will print John again. So if I run this now, you'll notice the output over here. And similarly, there are many other data structures already available in the .NET framework under the namespace system.collections.generic. And we also have the ability to create our own custom implementations as well, like the one which you just saw. In this lecture, we'll be taking a look at one of the examples of linear collections with direct access. The data structure that we'll be discussing today is called jagged arrays. Jagged array is an array of arrays where each row of an array is made up of an array. Each dimension of a jagged array is a one-dimensional array, and we call it a jagged array because the number of elements in each row may be different. So here, if you take a look at the example that we have created two single-dimensional arrays called Jan and Feb. Based on the number of days in each month, we have the array dimension specified. So this one is going to have 31 and this is going to have 29 values. Now we are creating a jagged array. The syntax of it, as you can see, if it is a jagged array, you need to specify it in this order. So we're calling it as sales, and then we are specifying the number of elements that this jagged array will have. Here, as you can see, we are just targeting 2 months, Jan and Feb. We have mentioned it like this. Now what we are doing is, when these arrays will be initialized, the first week of each month, we are targeting the sales. So here you can see from 0 to 6 for the Jan month and for 0 to 6 for the month of Feb, we are assigning total number of sales that happened. And here we are looping through each month, so we know that there are only 2 months. That's why we are looping from 0 to less than equal to 1, and then for each month we are doing a total. Now the total is dependent on each month's sales, and as we know that we are only taking first week of each month, so here we are looping through 0 to 6, and then we are adding it over here, month and day, and once it has been added, we are updating the total, and finally we are calculating the average on week. So average, that's total divided by 7 per week, and here we are saying average sales for the month. Now let me run this and show how it is working. Here you'll notice Jan is now having 31 values, so you can see it's starting from 0 to all the way up to 30. Similarly, for the month of Feb, you'll notice that Feb is having 29 blocks over here from 0 to 28. Now when we are creating this jagged array, you'll notice that the syntax is the data type of the array will be there, and then we have these two square brackets. After that, again we are initializing it with new int, and here we are providing the total number of items that this jagged array is going to have. Now the first bracket that you see over here represents rows in the jagged array, and the second square bracket that you see represents the item position in each row. To further elaborate this, you can see over here as an example, we are saying that sales for the month of 0 represents the month Jan over here. So we are saying sales for the month of January, and then this is the first day of the month of January. Then over here, this is the second day, third day, fourth, fifth, 6th, 7th. So that way we are covering the first week of January over here. So this 0 represents the row and this represents the item position in that row. Here we are talking about for the month of February, and same number of days are mentioned here as well. Now we are saying average sales for the month, but over here you can see that we are just dividing it by 7. So using this example, we are saying this as average sales for the month. But if we would cover all 31 days and 29 days for the month of Jan and Feb, and then this will become average sales per week for the month. Currently, as we are just capturing 7 days, we are saying average sales for the month. And here we have the result for the month of Jan and Feb over here. So that was jagged arrays in C#. In this lecture, we'll be looking at sorting algorithm. The first algorithm that we'll be exploring is bubble sort. Bubble sort is one of the slowest sorting algorithms that is available, but it is also one of the simplest sorts to understand and implement. That is why we are exploring this first, and then we'll see other sorting algorithms as well. The reason why we call it as bubble sort, because the values float like a bubble from one end of the list to the other end. Usually, if you are having a list of numbers, random list of numbers, the higher value will go to the right and the lower value will be at the left side if you see it in a horizontal sequence. Now, how this is implemented is you pick one number and you compare it with the adjacent number. If the number that you have picked is greater than the number with which you are comparing it, then the picked number will be moved towards right. Similarly, if the picked number is less than the adjacent number, then it will be moved left. So at the end of this sorting process, you will have lower values at the left side and higher values at the right side, and hence you'll have a sorted list of items. Over here, you can see that what we have done is we have used our existing collection, but this one is only going to work with integers. Here what we have done is, first of all, we have created 10 items and we have randomly added it to the collection that we earlier had. Here we are printing that collection, and then you can see we have our custom method called bubble sort, which is being applied on this collection. After that, we are printing the sorted number. Now let's go and see what exactly we are doing over here in bubble sort. The first thing that we are doing is finding the upper limit, and that comes by finding out the total count that we have, or the items that we have in the array -1. This is the temporary variable that is going to be used for exchange purpose or sorting purposes. And here we have two loops. First is the outer loop. So we're saying integer outer is equal to upper. So let's say if there were 10 items in the list, remember it starts with index position 0, and count is going to give you 10 if total number of items in the list is from 0 to 9. So that's why we are saying 10 minus 1, 9. Now upper limit will be 9 over here, and it is also being checked as if it is greater than or equal to 1. So basically we are running from 9 to 1 in that order. And then the inner loop is actually going from 0 to 9. And here we are comparing whether the value at these index positions in the inner list. So here inner is 0 and inner list plus 1. So we are comparing the adjacent values, and if the value is greater than the adjacent value, then we are exchanging it. And this process is repeated till we have a sorted list and this loop gets completed. So if I now go ahead and run this, you'll notice the initial list was having a random order, and here in the ascending order the bubble sort has sorted the list of integers. So 14, 15, 34, 35, 61, 66, 71, 90, 94, 96. And that's how easy it is to implement bubble sort in C#. this lecture, we'll be taking a look at how selection sort works. Now, the first thing that we've done over here is we have created a collection and randomly inserted some values to the collection, and then we are displaying it. Finally, we are applying selection sort on that, and here we are printing out the sorted list. Now, let's see how selection sort actually works. This sort works by starting at the beginning of the array, comparing the first element with the other elements in the array. The smallest element is placed in position 0, and the sort then begins again at position 1. Now, this process continues until each position except the last position has been the starting point for a new loop. As you can see, we are making use of two loops over here. The first one is here, and then we have other one over here. The outer loop that we have moves from the first element in the array to the next to last element, whereas the inner loop that we have moves from the second element of the array to the last element, looking for values that are smaller than the element currently being pointed at by the outer loop. After each iteration of the inner loop, the most minimum value in the array is assigned to its proper place in the array. So here we're comparing it. As you can see, if outer value is pointing to the first item in the list, then the inner one is pointing to its adjacent item, and then both are compared. As you can see over here, inner is the value, and then this min that we have over here, which is currently pointing to outer, so 0. So here we are doing a comparison. If the adjacent value is less than the outermost first value, then obviously we are saying that this is the new minimum, and here we are doing the sorting. Now let's save this and run it. So here you can see the sorted value is now appearing 14, 15, 34 till 96, and top you can see the random values being displayed. So that was selection sort in C#. In this lecture, we'll be exploring shell sort algorithm. This algorithm is named after its inventor, Donald Shell. It is basically an improvement over insertion sort, and the key concept in this algorithm is that it compares items that are distant rather than adjacent items, which is the case in insertion sort. As the algorithm loops through the data set, the distance between each item decreases until at the end the algorithm is comparing items that are adjacent. Shell sort sorts distant elements by using an increment sequence. The sequence must start with 1 but can then be incremented by any amount. A good increment to use is 3, and over here you can see that the increment, as long as it holds true, that is, it is greater than 0, in that case the logic keeps on repeating itself. So over here what we are doing is we are looping through from 0 to all the elements that we have in our collection. Then over here we have taken a variable j equal to I, so we are initializing j with the current value of I, and then we are trying to find out the value in the collection at index position I, and that is being stored in the variable temp. Then we are checking whether the value j is greater than equal to 3 or not, which is over here inc, and the value at index position j minus inc. So initially if you see 0 minus inc is minus 3, so this will not pass at all. But whenever the value will be there and the value will exist, in that case this swapping will take place, and finally we'll get a sorted list. So over here in our programs.cs file, we have just created a collection class, added random values to it, printed it, and then using the shell sort we are sorting it out. So let's run this now to see it in action, and here you can see the top list shows the unsorted list and the lower one is showing sorted list using shell sort. In this lecture, we'll be taking a look at how we can create our own collection using ArrayList. For that, we have created a class called collection, and if you see, it's inheriting from its base class called collection base. Now if I show you collection base, it has got this array list which we call as inner list attribute. Now using inner list, we can have our own collections. How we can have our own collections? By creating methods. For instance, here you can see I'm saying create a function called add, which will accept a parameter of type object, and that item will be added to this inner list. Now inner list is of type array list, which is provided by this abstract class collection base, and this one resides inside system.collections namespace. Similarly, once we have added the item, we can also remove it. Now removing an item is pretty easy. Similar to add, we have remove, where we accept a parameter of type object, and the same parameter is then passed to the inner list dot remove method of the array list, and it will remove that item from the array list. Then we have clear basically clear search all the elements inside the array list. So we will be back to square one, and the contents of the array list will be deleted. Count is going to return the total number of elements that are present in the inner list or our array list. Now to implement this, we'll go to our program.cs file, and here you can see I've created an instance of the collection class that we just created. Here we have the instance name as courses, and we are adding some courses to this collection: JavaScript, ASP.NET, MVC, C#, Python. Now using for each loop, we are simply writing the course names, and here you'll notice we are finding out how many number of courses are there in the courses collection by using the count method, and then we are removing one course from the list or the collection, and then we are checking out what is the total count. After that, we are clearing it out, and then we are checking out what is the total count. Now if I run this one in over here, you'll notice initially it's printing JavaScript, ASP.NET, MVC, C#, Python. Then when we were saying number of courses, so total courses at that point was 4. We removed Python from it, the count reduced by 1, and here number of courses 3. Then we called courses.clear, and here you can see now the number of courses is set to 0. So all the items from the collections have been removed, and that's how easy it is in C# to implement data structures. Now in the next lecture, we'll be covering generics. In the earlier lecture, we covered merge sort, and in this one we'll be covering quick sort. Just like merge sort, quick sort is also based on partitioning. Basically over here we pick an element dynamically, and in merge sort we kind of had the partition value predefined. In our example it was set to 3. Now here in quick sort we pick an element and call it as a pivot element. Using that pivot element we partition the list. Now there are many versions of choosing which element can be treated as a pivot element. In this example, we are treating the last element of the collection as the pivot element. In some cases, we can choose the first element as pivot, and in some other cases, any random value can be picked as a pivot element. Now, the key process over here is the partitioning. So basically, what we do is we pick a pivot element. We, based on that, divide the collection into low and high value sets. Now anything which is lower than the pivot element goes on the lower list, and anything which is higher than the pivot element goes on the higher set. And this process is repeated recursively until we get a sorted list. So over here we have two methods, quicksort and partition. Quicksort basically makes use of the partition. So if you see in our programs, we have a collection of numbers, and then over here we are doing the quicksort, and we are passing the collection, and then we are saying the low value is 0, so the first element is 0, and based on the index position, total minus 1, that is the last value in the list, and we are calling it as low and high parameters. Now we'll go inside this method quicksort, and what we are doing first is we are checking whether the value low is less than high, and if that is true, we are creating a partition. Now partition method accepts the numbers array low and high, and over here if I take you inside the partition method, you will see that first of all, based on the index position that high is representing, we are getting the pivot element and we are storing it over here, and then another variable is set as I, and that is being set as low minus 1. So in this case, I is going to be set as a minus 1. Now we are looping through low to high. So here you can see we have this for loop, j equals low, so low was set to 0, and j less than high, high initially was set to 10 as our collection had 11 elements. So it is going to run from 0 to 9, and here we are checking during this process whether the number at position j or index position j is less than pivot. Now pivot, as you can see, is the last element. So if this statement is true, we are incrementing the value of I, and then we are swapping or interchanging the values, as you can see. Now once this whole process is complete, we have another set of swapping to be made, and here we have created another variable temporary 1, and here we are saying numbers.get I plus 1. Now after this loop has completed, I will have a different value, and based on this index position, it will have a value over here, temp1, and then we say numbers.set I plus 1, numbers.get high, and similarly numbers.set I temp1. So let's go ahead and run it one loop to see it in action. So I'll be running it now. Over here you can see low is currently 0, high is 10, and this is the array collection that we have, total of 11 items in it, and these are the items that we have in our collection. Now as this condition is set to true, we'll be going next, and here you can see we are going inside the partition method. Let's go inside the partition method now, and here we have a breakpoint already, so we'll hit it over here, and if I move next, you will see the pivot element is set as 96, and that is the last element in our collection. Now let's move further. So here you can see current value of j as of now is 0, and if I say numbers.get j, and let's do a quick watch over here, it is returning 96. So value at j is also 96 over here, and the pivot value is also 96. Now this condition obviously is not going to satisfy, so what it will do, it will simply skip this thing altogether. Let's have another breakpoint set over here, and as you can see, the value of j keeps on looping through, so currently it's set to 1. Now if you see the value at index position 1 in the collection is 15. Now 15 is obviously less than 96, so here it will go inside this loop, and it will increment the value of I over here. Let's have another breakpoint and click continue. So the value of I is now set to 0, and here if you see numbers.get of I, so at index position 0, the value that we currently have is 96, and that is what will be assigned to the variable temp. So let's move ahead, and here you can see the variable has been assigned the value 96 now, and then what we are doing, we are setting the value at index position 0. So I is set to 0, and numbers.get of j, if you see, is 15. So if I do a quick watch over here, this is the value. So this is what we are setting at index position 0 now, and once that's done, let's move to the next line, and if I now show you numbers, and here inner list, you'll see at index position 0 we have 15 and temp is having 96. Now at this index position we'll be swapping out it with temp. So let's proceed now and finally see what is the status. So here you can see at index position 0 the value is 15 now, and at index position 1 it has been swapped with the temp value 96, and once that's done it will continue its process, and finally when it will reach at this point, you'll notice the value of I is currently set to 8, and here we are trying to get the next item, so I plus 1, and if I show you using quick watch, this is the value we are getting at index position 9. So that value is then stored over here inside the variable temp1, and then again we do this swapping over here, as you can see. So at index position 9 we are setting the value stored at this index position represented by the value high. So let's see, doing a quick watch, this also is currently 96, and if I see the value of high over here, you can see it's index position 10. So that value is then stored over here at index position 9, and we are again doing a swapping. So at high we are again setting temp 1. So after doing that, it is going to return this value I plus 1 as the pivot value. So now if I go and take a look at numbers over here in a list, you'll see 15, 66, 90, 35, 94, 71, and here 96, 96. So this process will keep on repeating until we have this condition, low is less than high. So as soon as this condition is false, we'll skip it and we'll have our sorted list. So let's run it completely now to see it in action, and there you go, you have the sorted list now coming up: 14, 15, 34, 35, 61, 66, 71, 90, 94, 96. So that's how quick sorting works. In this lecture, we'll be exploring searching algorithms. The first one in this is sequential search. Now over here we have created a collection and then obviously inserted 10 random numbers to that collection, and now we have created a method called sequential search, and here you can see that it is expecting a parameter integer value, and here I'm just inserting a value called 96, or passing a value called 96 over here, and we are trying to search whether this number exists in the numbers collection or not. Now let's go ahead and explore how sequential search is working. So over here you can see we are looping through index position 0 to the last index position, and when we are doing that we are also checking whether the value that has been passed resides at any index position or not, and whenever it is found it returns from there and skips the remaining item in the list from being compared. Otherwise you are seeing that it returns false, and we say that this value does not exist in the numbers collection. Now if I execute this program over here, let's run this, and you can see it's resulting as true. Now let's give one more number over here by stopping this, and here we'll be passing 106. Now let's run this again, and here you can see the list of numbers that's there, 96 to 14. We are getting this value result as false because there's nothing in the list which is going to match with the value that we have passed, 106. So basically in sequential search we go from one item, like the first item in the list, to the last item, and wherever the result is found we return from that and say that the item has been found. Otherwise we go to the end of the list and finally return saying nothing was found. In this lecture, we'll be taking a look at binary search algorithm and how binary search is implemented. Now, In order to understand binary search, consider a sorted list of 1 to 100. And let's say you are given a task to guess the number or search the number, let's say 82. In that case, what will happen is your first guess should be the midpoint. So between 1 to 100, you have the midpoint as 50. So if you've guessed 50, you'll then compare 50 with the searched value, if it is lower or higher. If it is lower, then in that case, you'll know that the value is higher than the one that you have guessed. So in that case, you have a new list from 50 to 100. Now again, in that, you'll have a midpoint like 75. Now, when you'll compare 75 with 82, again the value will be low because your value is 82, which you need to find. So in that scenario, you'll have the list further shortened from 75 to 100. And in that case, you know that the value exists in that particular list or subset. So you'll again find a midpoint, and from there you'll compare the value that you need to search. And if it is lower, you'll further shorten the list, and if it is higher, you'll again have the list bifurcated based on that. So here what we'll be doing is, let's say we have to search 96. The first thing that we did is applied selection sort so that we have everything in ascending order from 1 to 10, let's say. And then inside the binary search, if I show you, what we are doing is we are having 3 variables: upper bound, lower bound, and mid. So upper bound is the last item in the array, lower bound is the first item in the array, and then we are comparing whether lower bound is equal to or less than the upper bound. If that's the case, then here we are trying to find a midpoint. Like I said, if the list is between 1 to 100, then the midpoint will be 50. So that is what we are calculating over here, and then we are comparing the mid value with the value that we need to search. So here is the value that we have passed, and if it matches, then obviously we are returning the mid value. If it doesn't, then it will go to else if block, and here we are saying if the value that is being searched is less than the middle value, in that case we are shifting the upper bound to mid -1, else we are shifting the lower bound to mid +1, and then the search is again performed using the while condition. So as long as this lower bound is less than equal to upper bound, this loop will go on, and wherever the value is found, it will be returned. So let's go ahead and run this now. So here I'll be running it now, and here you can see we are getting the index position now. Wherever the first occurrence of the value is found, we are showing it over here. So if you see index position 9, if you count from here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that is where the first occurrence of the searched term is found, and that is what we are returning, the index position where the number was found. And that's how easy it is to create a binary search algorithm in C#. In this lecture, we'll be taking a look at how we can rewrite the binary search algorithm that we covered in the previous lecture. Now over here, what we'll be doing is we'll be enhancing our binary search approach by creating a recursive function. So if you look closely at the binary search algorithm, what we are doing in that is that we are shortening the list on every iteration. So it's like calling the same function but with different values, and that's what we have done over here. If you look closely, the new method that we have created, recursive binary search, it now accepts 3 parameters. One being the value which we have to search, and the other 2 is lower and upper value. So initially, as we were saying, that we will have a sorted list, and the lower value will represent the first item in the list and the higher value will represent the last item in the list based on their index position. So here, index position 0 refers to the first item in the list, and numbers.count -1 represents the upper value in the list or its index value. Now what we are doing over here in the recursive binary search is that first thing, we are checking whether the value that we have passed is less than or equal to upper value or not. Now if that's the case, then we are going and finding the mid value. Once the mid value is there, we are checking whether the value that we are searching is less than the mid value or not. And if it is less, then we are doing a recursive search, and in this case you can see that the upper value gets modified or updated. So now a shorter list is being searched. In case the value is right there, then obviously the index position is returned and user is made aware that here's the index position where the value exists. If that's not the case, then we are again doing a search, but this time the list is updated, and here you can see the lower value is now updated as mid +1. If this condition itself is not true, in that case we are simply saying that there's no way we can find this value in this list. Basically, the value does not exist. So let's go ahead and run it now. And as you can see, the result is coming up at index position 9. So if you count from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So the first occurrence of the value 96 in this list is at index position 9. And here's how we have achieved it using recursive binary search. In this lecture, we'll be exploring another data structure called stacks. Now, stacks is based on LIFO principle, that is last in, first out. And here it involves two kinds of operations primarily. Push is used to add items to stack, and pop is used to take items from the stack. Now in this one, we have created a custom stack. Even though C# does provide a stack data structure, we'll be reviewing that as well. But just to understand the nitty-gritties of a stack, we have created our own implementation, and here you can see the stack class. What we are doing is we are making use of the array list to store items in the stack, and here's the constructor that we have. We are initializing the array list, and then we have count, which is going to return total number of items that is there in the stack. Then we have push, which is used to add items to stack, and we have pop to take out the item from the stack, and then we have clear, which is going to clear out the list, and peek is going to give you topmost item that we have in the list. So here what we are doing is, first of all, we are creating set of numbers and adding it to the numbers stack one after the other, and that's where push operation is called. Here you can see number.push is the method that we have used. After that, we are doing a pop operation in which we are popping out one item from the stack, and then we are counting the total number of items in the list. After that, we are doing the peek operation, and finally we are clearing out the list and seeing what is the exact count remaining now. So let's run this first and see it in action. So here you can see the push operation, and after that we are doing a pop, which is giving you the value 96. So that was the kind of last item inserted in the stack, and that's the reason why it was shown first or popped out first. Total count, as you can see over here, is 10, and here we are adding 11 items. So you can see 0 to 10 less than equal to 10. So after popping out, the total number decreased to 10, that is one less. And here we are doing the peek operation. So the next item in the list after popping out was 14, and that is what we showed over here. And then we did our clear operation, which was kind of resetting the whole stack by removing every item in the list. And here's the final count that is coming up after the clear operation, that is 0. So let's go ahead and do one more change over here before we move on to the stack. So here what we'll do is, as you can see, we have added these numbers. We'll do a count over here as well. So after adding, let's go ahead and do a count. So here's the total count. Now if I run this, so you can see the push operation has inserted 11 items, and after popping out, the total count is now 10. So that's what I was trying to explain. And now let's go ahead and see how we can make use of the built-in stack class, which is provided by system.collections.generic namespace. And here you can see we have stack. And remember, when we were discussing generic, we mentioned that there is a template which we can use to create a specific kind of collection. Now here the collection that we are creating is stack, and this is of type string. Now if I take you to the stack definition over here, you'll notice that we have few methods, like you can initialize a stack, empty stack, or you can initialize it with a capacity or a collection. And then obviously we have the count method, which is going to return the total number of items in the stack. And here we have peek and pop that we just now explored in our custom implementation. Similarly, we have push. And apart from these common methods, we also have some add-ons. For instance, you can convert the stack to array, and here you can do a copy to. You can search for one item based on contains, and then you have the get enumerator implementation to do a for each kind of loop on the stack. So this is what we are having in C#, the built-in stack implementation, and this one which we just now explored is the custom and pretty basic implementation, just to understand the idea behind the data structure called stack. In this lecture, we'll be covering queues. A queue is a data structure where data enters at the rear of a list and is removed from the front of the list. So basically, it's like first in, first out. The two popular operations on a queue are enqueue and dequeue. Basically, queues are used to store items in the order in which they occur. For instance, queues are used to order processes submitted to an operating system or a print spooler, and simulation applications using queues to model customers waiting in a line. So here we have created a custom queue implementation, and then obviously we'll be also exploring the one which is provided by the .NET framework itself. So here we have created a queue class, and if you take a look at it, the queue has got these functions: enqueue, dequeue, peek, clear queue, and count. We are obviously making use of the array list to create this queue data structure. Now enqueue is responsible for adding item to the queue, and dequeue is responsible for removing the topmost item from the list. And here we have peek and clear queue. So basically it's going to clear all the items from the list. Count is going to return the total number of items in the queue. Now if I have to use this over here, you'll notice that we are doing the same operation which we did for stack, but over here it's like adding it to the queue. So we are making use of the enqueue operation. Later on here we are removing one from the list and we're printing it over here. So numbers.dequeue, and then we are doing a count. If the item has been removed, what is the total number of items left in the queue? And then here we are using the peek operation, and finally we are clearing the queue and then doing a total count. And here the one which is provided by the .NET framework itself inside this namespace system.collections.generic queue. If I take you there, here you can see exactly like stack, we have three constructors: empty one with capacity and the other one with a collection. Then we have count, clear, and some additional methods like contains and copy to. The popular ones, enqueue and dequeue. Get enumerator is there to loop through the items in the array, so that you can make use of the for each kind of loop. And then we have peek to convert it to an array. We have to array method, and then we have trim access. So that is what we have from the system.collections.generic namespace. Now let's go ahead and execute this and see it in action. So here you can see the enqueue operation has been performed, and total number of items in the list is 11. And then we are doing a dequeue operation, so item 96 was removed from the queue. Total count after that stands at 10. Then we did a peek operation, so next item in the queue is 15. We are then clearing it out, so the total count becomes 0. And that's how easy it is to create a queue in C#. In this lecture, we'll be taking a look at dictionary data structure. Basically, a dictionary is a data structure that stores data as key value pair. And in .NET Framework, we have dictionary base class, which is used as an abstract class to implement different data structures that all store data as key value pairs. And in this example, we'll be taking that into account to create a custom implementation of the dictionary class. So here we have created our own implementation of the dictionary class, and as you can see, it has got the bare minimum requirements. First being the add method, which is kind of adding from the dictionary base in a hashtable.add, and the key that we have defined. So the key is over here, name, and value associated with that key is fee status, and that is what we are storing inside the hash table. And then here we are getting the item based on the key, and since key is name over here, that's why we have the parameter name as name. Similarly, for remove, we have the remove method, and here we are passing the key, and based on that key we are removing it from the inner hash table collection. Now over here I have created an instance of the dictionary class that we just created, and here using the add method we have added 3 students and their fee status. Finally, we are writing it over here based on the total number of items present in the dictionary. The count shows that, and here we are trying to find out one specific item based on the key value. So here the key is John, and its value will be coming up as due, and then we are clearing out the dictionary collection that we have. Here, if I show you, this is the data that we are getting. So it says there are, if you see over here, there are 3 students, and then we have this John's fee status as due. Now here, the other implementation that C# .NET Framework provides is the system.collections.generic dictionary, and here you can see we can specify the key value pair, like over here we did for string and string. Here we can have something like string and boolean. So if I take you to the implementation over here, the generic dictionary, you can see there are some overloads of the constructor like dictionary. Then you can initialize with capacity, you can provide an equality comparer, then you can have a dictionary with key value pair, and some more. Then here, if you see, you can get the count of it, you can just get the keys, you can just get the values. Here you can add items, you can clear one, you can use the search based on contains key, you can search based on contains value. Then you have the get enumerator implementation, so that you can loop through the key value pairs in a dictionary. Here you have the remove method, and some more. Okay, so here we just explored how to create a dictionary object in .NET Framework using C#. In this lecture, we'll be exploring hashing and hash table. So basically, hashing is a very common technique for storing data in such a way that the data can be inserted and retrieved very quickly. And in order to implement hashing, we make use of hash tables, and hash table is provided by default in the .NET Framework library. It resides under the namespace system.collections. So here you can see some of the constructors for the hash table that we have, and some of them that we will be utilizing is this one. So you have a default hash table, and then you have a hash table where you can specify the capacity. And if you just explore this, you'll find that capacity basically means the approximate number of elements that the systems.collections.hashtable object can initially contain. So here in our code, if you see, we have created a hash table with 25 as the capacity, and here we are adding some keys to it like salary, name, age, department, and one more way of adding key value is using the index syntax. So here we are saying symbols, and then we are specifying the key and then the value associated with it. After that, we are looping through all the keys that we have in this hash table, and then we are showing all the values that we have in this hash table. And finally, here if you notice, we are showing the key as well as the value that it contains. So you can see, in order to retrieve a value, you can use the index syntax, so symbols, and then you provide the key name, and that will give you the value associated with that key in the hash table. So let's go ahead and quickly run this to see it in action. And here you can see the keys are being printed first: name, salary, gender, department, age, and then the values over here: David, the salary, male, that's the gender, information technology, and then 45. And here you can see the key value pair being printed together. Now let's go ahead and take a look at some of the utility methods that the hash table class provides. So we have over here a method called count, which is going to return total number of items that are present in the hash table. Then we have clear. This is going to remove all the elements of a hash table. And if you want to remove a single element from a hash table, we can make use of the remove method. Here you need to provide the key, and the key value pair will be removed from the hash table. And then we have this contains key, which is used for finding whether a key exists or not. So you can use this before removing an item from the hash table or key from the hash table. Similarly, you have contains values, which is exactly what contains keys for key, and it also gives you a boolean result whether it's present or not. So if you say this key is existing or not, if it exists, then you can obviously move ahead and remove it. Similarly, if you want to find out whether a value is there in the hash table or not, you can use contains value, and it will return either true or false. So that was hashing and hash table in .NET Framework. This lecture will be covering a new data structure called linked list. Now, there are a variety of linked lists that we can implement, but .NET Framework provides doubly linked list data structure. So linked list is like there are nodes, and each node points to the next one in the list, and that's how they are linked, because one node contains information about the other node. The doubly linked list, on the other hand, allows us to traverse back and forth. So a normal linked list will allow you to travel from first node to the last, but a doubly linked list will allow you to travel from front to back and back to front. And then we have another variety of linked list called circular linked list. In that, the last node contains information about the first node, so in a way they are connected together. So the first one will connect to the next, and the last one will connect to the first one, and that's how the circular linked list is created. Now here we will be exploring the doubly linked list, which is provided by .NET Framework. Now there are two parts to linked list. One is called the node, and the other one is the list itself. So over here you can see we have this linked list node, and we are creating one node at a time. This is a generic implementation, so here we have to specify what kind of node we are creating. This one is a string node, and here we have provided the name John. So this is a node, and then we have created a linked list. You can see that it comes under system.collections.generic linked list. So under the system.collections.generic namespace, we have this data structure called linked list, and here also you have the generic version. So we are saying this list is of type string. Then what we are doing is we are making use of the add first method, and using add first we are adding the first node to this linked list called names. After that, we have created another node called node1, which is having the value Matt, and then we are adding that using the add after method. Now add after, if you see, contains two parameters. First one, which is the node after which you want to insert. So we are saying after node we want to insert node1. So in a way we are establishing a connection from John to Matt. And then we have created another node called node2. Here also we are using the add after method, and this time we are saying add it after node1. So now Matt and Mike are connected. Then we have just created a node 3 which is not doing anything at all. It is a null value. And after that we have created a new node called a node, and in this a node, from the linked list we are assigning the first value to this node. So basically we are saying assign John to this node, and here we are checking while a node is not equal to null, keep on printing the value that a node contains. And after that we are assigning the next item that the a node is pointing to. So if you look closely over here, what we are trying to do is we are assigning John to a node, and then we are assigning the next item that this is pointing to. So we connected John with Matt, so the next item will be Matt, and when we say Matt, the next item the Matt is pointing to is Mike, and that way the whole list will be printed out. We can also find out values using the find method that the linked list provide, and here you can see we are trying to find a word David, so this is not going to work. But if I go ahead and change this to, let's say, Matt, and then say anames.find Matt, obviously it is going to find Matt, and then the value will be assigned to this a node. And here when we say a node equals name.first, again we are pointing John to this a node, and again the same loop is being printed. So that's how you can traverse, add items to a node, and find node values in a linked list. Let's go ahead and quickly run this to see it in action. And here you can see John, Matt, Mike, and then again John, Matt, Mike is being printed. So that was linked list in .NET Framework. In this lecture, we'll be exploring a nonlinear data structure, and the most common example of a nonlinear data structure is a binary tree. A nonlinear data structure is used to store data in a hierarchical manner. And talking about binary trees, the benefit of this over traditional data structures like arrays and linked lists is that one can search a binary tree very quickly, and at the same time one can also insert data and delete data quickly from a binary tree as opposed to an array. Let's first of all understand the definition of a tree. A tree is a set of nodes, as you can see from this example. Each node is connected by edges. So here we can see that in binary tree, the topmost node is called the root node, and every node can have maximum 2 child nodes. As you can see over here, node 8 is the root node, and it has got 2 subnodes or child nodes, 3 and 10. And in the example you can also see node 14 is having just 1 child, that's 13. So maximum a node can have 2 child nodes. So a node can have 0, 1 or more nodes connected to it. And binary tree, as per its name itself, restricts it to 2 nodes per child, or to 2 nodes per node. If you want to further analyze it, a tree can be broken down into levels. Let's call it as a root node as a level 0 or at level 0. And then at level 1 we have these 2 child nodes 3 and 10. Then at level 2 we have child nodes 1, 6 and 14. And then at level 3 we have child nodes or nodes 4, 7 and 13. One more way of looking at this binary tree is that we can divide this into left and right portions. If you see from the root node, there are 2 clear separations, nodes appearing on the left side and then nodes appearing on the right side. So for 8, the left child is 3 and right child is 10, or left node is 3 and right node is 10. And the example that we will be exploring will be binary search tree, in which we'll be exploring how these left and right nodes play a crucial role. A binary search tree is made up of nodes. So here, as you can see, we have a node class, and if I explore this, you'll find out there are a couple of items or attributes in this class. They are data, and then left node, right node. And then we are also having a method called display node, which is going to display the data assigned to a given node. So now that we have our node defined, we'll be now taking a look at how we can create our binary search tree. So here's a class called binary search tree, and we have a root node. So if you take the look at the example that we had, this is the root node. 8 that we see over here is the root node, the first item in the binary search tree. So that will become the root node. We have a constructor which initializes a root as null. Then, in order to add items to a binary tree, we have this method called insert. So what we are doing over here, we are sending a value. Let's say we are sending 8 to this method as the first value. So that will be assigned as root node. Now let's see how it does that. First thing, we have created an instance of the node class. Then using the data attribute of the node class, we are saying this is the data which this node is going to have. After that, we are checking it if the root node is null. In that case, the new node that we have created becomes the root node. So here we have our root node defined. In case root node was not null, in that case we would have to look where exactly this particular value will go, whether to left or to right. So here in this example, if you see, there are two places where it will go. So left is 3 and right is 10. So in case this root node was already defined, then it would be further searched where this particular value will be inserted. In this scenario, let's assume if root node was occupied, then we'll have to find whether left node is available or not, and if that is also occupied, then we'll have to check about the right node, and if it's available, the value will be inserted at that position. And that's what we are doing over here. You can see here we have taken the root node as the current node, and then another variable called parent has been defined. After that, we are assigning current to the node parent that we have defined over here. And what we are doing, we are checking whether the value I that we have to insert is less than the current data. So if you see 8 was the root node, and if let's say 3 is the value that we have to insert, what we'll do is we'll come over here, we'll see 3 is less than 8. That's true. So the lower values are kept on the left side or left edges, and the higher values are kept on the right side. So here, if you see 3 is less than 8, in that case, it will go to the left node, and current.left becomes the current value, and then again we check over there if that node is empty or not. If it is, then we make parent.left is equal to new node. So the value 3 will then be inserted on the left hand side. If that's not the case, that is left is already occupied, in that case we'll go to right, and there also we check whether it's empty or not. If it is empty, then we put that new node as the right node for that particular parent. And that's pretty much it in order to insert a particular node in the binary search tree. Now there are a couple of ways to traverse the binary tree. Primarily we have in order, pre-order and post order. If you look closely, in order is something which is going to print the value in ascending order, that is from low to high. So in that case, you'll notice that we are storing the lower values on the left side and higher values on the right side. So what it is going to do is it will first of all traverse left nodes and then display the data, and then traverse the right node and display the data. So that way it is going to show it in the ascending order. Then in pre-order, if you see, it is going to traverse left then right. So currently whatever node position it is on, it will display that, and then from there it will traverse left once and then it will traverse right once. In that sense, it is going to traverse. The only difference between in order and pre-order is that you can see the display is happening prior in the pre-order, and here it's kind of sandwiched between left and right traversals. Then we have this post order where first of left nodes will be searched, and then after that the right ones, and then we display it over here. Apart from this, we have a couple of methods as well to find out the minimum and maximum value present in a binary search tree, and that we basically do Using the left node, we have all the minimum values, so we'll just traverse the left nodes to find out the minimum values, and if you have to find out the maximum values, we'll traverse the right node only. So you can see the difference now that we know where exactly the maximum values resides, the minimum value resides, and based on that we can say that binary search trees are faster because we certainly know where to find certain kind of values, like the maximum ones will reside on the right side. And here we have created one more method called find, which is just going to find a node based on the key that we have provided. So if the key is less than the current data, it becomes the left becomes the current value, and if it is greater than, then the right becomes the current value, and if there's nothing, then we just return null, and if we found something, we are returning that particular node. Now let's go ahead and see all these things in action first, and then in the next lecture we'll see how to delete nodes from a binary search tree. So here you can see that I have created a small example wherein we are specifically mentioning what values we are trying to insert, and the reason behind this to explicitly mention the value so that we can see how the traversal is working when we print out the results. Now here the insert method, I have made a few more changes, so I would like to first explain what changes were made and then I'll take you to the demo. So initially what we were doing is, like when we were traversing from the root node to left and right, in the explanation I forgot to write some more code to change the current value from root to the left and right ones. For instance, if you take the example over here in program.cs, first of all we are inserting 23, so this gets inserted as a root node. Then we are trying to insert 45. So 45 will be inserted on the right because it is greater than the root node value 23. After that, we are inserting 16. So when we'll try to insert 16, 16 will go on the left side of the root node, that is 23. So now we have a root node with 23 and two values, 16 and 45. 16 on the left, 45 on the right. After that, when we try to insert 37, 37 will be first compared with the root node. Obviously 37 is greater than 23, so it will go towards the right. Now right is already occupied by 45, and that is where I messed out the code to change the current position from root to the next one. So now that here in the code you can see that we are checking if the value that is being inserted is less than the current data, then we are going to the left basically, and if that's not the case, then we are going to the right. Now once we are on the left side, at that point we are making the current.left as the current. So let's say we are on 16, 16 becomes the current value or current node, and then if it is already having a value, then it will go and change it from 23 to 16. So here the parent is now 16 and current.left will point to the left of 16. So if that's null, then we'll insert the value over there. If that's occupied, then we'll go to the right of that node. So that's how it is right now, and let's run this now to see it in action. Over here you can see in order traversal is actually printing it in ascending order, so 3, 16, 22, 23, 37, 45 and 99 are being printed over there. And in pre-order traversal you have 23, 16, 3, 22, 45, 37 and 99. And then on post-order traversal you have 3, 22, 16, 37, 99, 45, 23. The min value, as you can see, is 3 and max value is 99. Using the find method we were able to find the node here 99.data. So that also got printed. Now in the next one we'll be exploring delete functionality in binary search tree. In this lecture, we'll be taking a look at how to delete a node from a binary search tree. The example that we'll be taking here is deleting a node with children. So you can see that we have created a method called delete node, and then we are passing the root node itself in the method. And over here, if I take you to the delete node method, what we are doing is we are first of all creating a node instance and then assigning the value that we want to delete as data. After that, we are calling this method called delete, where we are passing the root node and then we are deleting it. Now here the root node is already defined as an attribute, and that is how we can pass it directly over here. And then the instance that we create a delete node is being passed to this method called delete. Now if you come inside this method, here we are checking if root is null. In that case, we are returning root itself. So this is not going to delete anything if the root is null. Now, after that, we are checking if the data that we want to delete is less than the root data. In that case, we are going and calling the delete again, and this time we are getting the root.left. If the data that we want to delete is greater than root.data, then we are doing this operation, and this time we are saying root.right. After that, if the data that we want to delete is found to be root data itself, so what we are doing is we are going inside this, and here we are trying to find out whether there is any child nodes or not. So in order to find out child nodes, we are checking root.left and root.right. Now in this case, our root node is having two childs, 13 and 45. So in this case, this condition will not get executed. Over here, this will also be skipped because root.left is not null in our case, and here also this will be skipped. Now, as we have both the child nodes, what we are doing is we are taking the root.right.data. So in this case, 45 will be assigned over here, and that will part of the root.data. So 45 becomes the root node now, and then we are deleting the value that we have passed, and after that we are finally returning the data. So now if I run this one, here you will see when we have deleted a node with children, in order traversal now shows 3, 16, 22, 45, 37, 99. Earlier you can see that it was showing 23 as well. Now 23 has been removed from the delete node, and rest of the items or nodes in the binary search tree are displayed over here. So that's how we delete a node from a binary search tree. In this lecture, we'll be discussing a new data structure called set. A set is a collection of unique elements. The elements of a set are called members, and the two most important properties of sets are that the members of a set are unordered and no member can occur in a set more than once. A set is defined as an unordered collection of related members in which no member occurs more than once. A set that contains no members is called empty set. The universe is the set of all possible members. Two sets are considered equal if they contain exactly the same members. A set is considered a subset of another set if all the members of the first set are contained in the second set. On this data structure, we can perform union, intersection, and difference. Union is basically a new set is obtained by combining the members of one set with the members of a second set. Intersection, this also produces a new set by adding all the members of one set that also exists in a second set. Then we have a difference, which results in a new set by adding all the members of one set except those that also exist in a second set. Intersection operation and union operation are commutative, which means that set 1 intersection set 2 is equal to set 2 intersect set 1, and the same is true for the union of the two sets. Intersection and unions are associative as well, which means set 1 intersection set 2 intersection set 3 is equal to set 1 intersection set 2 intersection set 3, and this holds for union as well. Now some of the operations that I'm discussing will be more relevant when we'll be covering it with an example. So over here, we have created a set class using the bit array data structure. We have a constructor which is initializing the data with 5 bit array elements, and then we have some methods over here like add to add items to the bit array data collection that we have, and then we have isMember, which is going to find out whether a particular value is part of the collection or not. Then we have remove, which will remove the item from the set. We have union, which is, as I mentioned, is obtained by combining one set with the members of a second set. So that's what we are doing over here. We're combining one set with the other. So this is the current set and one we are passing over here, and together we are combining it, and then we are combining it and returning as a new set. Then we have intersection and difference that we just discussed, and then we have is subset function, which finds out whether a particular set is a subset of a given set or not. And then this one is the toString method that we have over here. Now in our program.cs file, we have created a set called set A, and here you can see it is having 3 items in it, or members in it, 1, 2 and 3. Then we have created another set, and this has got 2 members, 2 and 3. A new set has been created called set C, and here we are doing union operation. So you can see we are kind of adding 2 sets, set A union set B. So the new set C that we have over here will have all these values 1, 2, 3. And when we'll print it, this is going to print the values of set A 1, 2, 3, and set C will be printing 1, 2, 3. Next, what we are doing is we are updating set C by the intersection method. Intersection, as I explained, generates a new set by adding all the members of one set that also exists in a second set. So if you see, set A and set B have got these values 2, 3, 2, 3. So set C will have that value, and then the same will be printed. Then we have set A difference, set B. Difference, as I mentioned, returns a new set by adding all the members of one set except those that also exist in a second set. So if you see set A and set B over here, 2, 3, 2, 3 exists in both set A as well as in set B. So the difference operation will result in a new set with value 1. And that is what we will get in set C over here. Finally, we are trying to check whether set B is a subset of set A or not. And if it is, then we are printing this line B is a subset of A. Otherwise, we say B is not a subset of A. So let's go ahead and see all these in action now. So here you can see, first it is printing set A values 1, 2, 3. Then it is printing set C value. With the union, we were getting this value 1, 2, 3. Then for intersection, we were getting 2, 3. And for difference, we were getting 1. And then finally, with the is subset, we're getting this B is a subset of A. So that was sets in data structure using .NET Framework.